Okay, we got into chapter 12 kinetics last time, and we talked about a couple things. We talked about the again rate expression, and remember with the rate expression, we can really figure out how anybody in the reaction is changing with time. If we pretty much just know one piece of information. So again, if we had say a reaction such as this, we could write the rate is equal to. Remember, as we talked about, the reactant should be decreasing with time. So we do represent that with a negative there on the reactant side. And we also do have to take the stoichiometry into account, as we also discussed, which would be 1 over our coefficient. And again, that'll take care of all the kind of mole to mole relationship in the equation. The change in the concentration of A over the change in time. We could set that equal to our other reactant, also going to be negative because it's decreasing with time, 1 over the concentration, 1 over the coefficient, change concentration of B over the change in time. And we can also set that equal to our product. Once again, our product should be increasing with time, so we do not do the negative. And again, we still take 1 over the coefficient to take care of the stoichiometry, change in concentration of C over the change in time. Again, the reason we have the negative here, as we talked about, is when you do calculate the average rate, it should be a positive number. And for our reactants, our final concentrations are going to be basically less than our initial concentrations. And that's going to give us a negative value when we do the change in concentration part. So that negative and negative will turn the rate into a positive. Remember as well that if you are solving for just a reactant, how that reactant is changing with time. You will end up with a negative value for that because it's decreasing with time. Just like you should end up with a positive value if you're figuring out how the product is changing. We then got into the rate law, which is a little bit different. The rate law has a generic sort of setup of the rates equal to K times A to the X and say B to the Y if we just have two reactants. This is the rate of the reaction, obviously, meters per second, molarity per second, or something of that nature. That is our rate constant. And as we talked about last time, you can kind of think of it as how fast or slow the reaction will take place. So kind of the larger the rate constant, the faster the rate of the reaction. You can just think about that in just mathematical terms. Obviously, we're multiplying what's on this side by that number. So if it's a larger number, that's going to end up with a larger rate when it's all said and done, right? If it's a much smaller number, we would end up with a smaller rate for that reaction. Now, a couple other things in here. First off, the rate law only deals with reactants. So there are no products in the rate law, so it's all about the reactants only. The X and the Y here are what are known as orders. And one of the first important things that we talked about, I think, last time as well, is they are not from the coefficients in the balance equation. So that is not how we get those. We're going to talk about how we get those in just a second, but they are not taken from the coefficients. They are sort of like the proportion of each of those reactants that you need to maintain a particular rate. And one of the things that we talked about at the very end there was, again, the usefulness of a rate law is, again, if you're doing a reaction or something in person, and maybe that reaction, as I mentioned last time, is maybe just running way too fast for you to kind of take measurements and stuff like that. You can use the rate law if you know what it is, and especially if you know the orders of the reactants to modify your experiment. And you could, for example, slow it down if you kind of need a little extra time to take your measurements and stuff like that. You could also do the opposite, which is you could speed it up if you needed to kind of speed it up. And as we talked about, I think it started on that side. We're going that way. I think. Thanks. As we talked about last time, for example, if we had a rate law where A and B were both first order, and again, just like in chemistry, we don't write the one, but if you do not see anything up there, it is first order for each of them. And basically, we could change either of these reactants, and it will have the same effect on the rate. You could double it or triple it or whatever you want to do. The concentrations are cut it in half. And no matter which one you choose, A or B in this case, because they're basically both the same order, they essentially will kind of do the same effect on the overall rate of the reaction. Now, if we had a rate law where maybe they both weren't first order, but maybe one of them was second order. In this case, B would have a much more dramatic effect on the rate of the reaction. So anything that you would do the B in terms of its concentration, increase it or decrease it, it would have a much bigger effect than if you wanted to do something with A. So in this sort of reaction here, maybe you do want to still increase the reaction, but maybe not as much as it might happen if you play with B's concentration. You could still play with A's concentration and achieve that increase in rate. It just won't be as big as it would happen if you kind of did it with B in this case, because of the order of B in this case. Now, we also talked about that if you add up the orders, the individual orders here, so that'll give you the overall order of a reaction. So in this particular case, the overall order here would be 1 plus 1, which would be second order reaction. Over here, it'd be 2 plus 1, and it would be a third order reaction in this particular case. First off, any questions on any of that stuff we talked about last time? Now, one of the things, since we're kind of looking at this here that maybe we didn't touch upon last time, is now what happens if I had, for example, a rate law where it was K, A, and B to the 0. So in this particular case, I do have a reactant where the order is 0 order for that reactant. When we take something to the 0 order or 0 power, what does it equal? It does equal 1. So in this particular case, this is the same as like the rate would equal K times A. Now, if I had this as the rate law for the reaction I'm looking at, and I like quadruple B's concentration, will have any effect on the rate? It will not. So in this particular case, you can do whatever you would want to be. It actually will not affect the overall rate of the reaction because it is 0 order in this particular case. If you wanted to affect some type of change, you would have to go look at A in this case to get it to increase or decrease or sort of change the rate of the reaction. So it is possible that you could have some reactants that are present. Their order could be 0. And basically what that means is it really has no effect on the rate. You could, again, do whatever you want to those guys. Any questions on that there? All right, then let's talk about these orders. Rate laws are found experimentally, basically. So when we talk about rate laws, they are typically found experimentally. So usually when you're going to try to determine sort of what the rate law is for a particular reaction, you oftentimes are given basically lab information, a table of data, and you're going to use that table of data to basically figure out what the orders are for each reactant and ultimately the overall order of the reaction. And then once you have sort of those things calculated, the orders, you can then actually calculate what the value of the rate constant would be for that particular reaction. So let's take a look at one and how we would approach this. Let's say we had this reaction here, and this is obviously the table that would be associated with the experiment that we performed. Here we basically have 3 experiments, experiment 1, experiment 2, and experiment 3 that they did. And this gave us some initial rates in these reactions here. And we can figure out the rate law by the data that's in the table here. And we could write a generic rate law for this, which is the rate is equal to K times F2, and I'm going to call that to the X, and ClO2 to the Y. And here really the goal is to figure out what X and Y is. Now, I would say probably for most people, it's probably a good idea to do it mathematically because you got to show your work. So that's probably the best approach to sort of figure out mathematically what is going on here. So to do that, you can use this sort of formula, this generic sort of formula, which is rate 2 over rate 1 equals K like A to the X, B to the Y divided by K, A to the X, and B to the Y. So let's talk a little bit about what these are. when we talk about rate 2 and rate 1 here, it doesn't necessarily mean you go to the table and you just choose the first one and the second one that's entered. Basically, what you want to do is go to the table and you want to find two entries in the table, basically two experiments that were done in this table where one of the concentrations remains the same and the other one varies. So the idea here in math, right, is to have as little unknowns as possible, right? So by doing so, by keeping one concentration the same and the other one varying, you will be allowed and be able to really calculate what you need pretty easily. So rate 2, rate 1 means go to the table and do that. And basically everything on the right-hand side there is just all the information from the table, basically, is what you're going to kind of pop in there. So let's take a look at this if we want to figure out the orders. So the first thing I'm going to do is go to my table here, and I'm going to look and find two entries where one of the concentrations remain the same. And you can probably clearly see here, 1 and 2 will achieve that for F2. So the concentration F2 stays the same in 1 and 2 experiment, and it varies in ClO2. So I'm going to look at experiments 1 and 2 here. I'm basically going to put my information into that sort of formula there. Now, one of the ways to do this where maybe it'll be a little easier for you, and you don't necessarily have to do it this way, but it will usually give you a little better numbers, if you will, not so many decimal points and stuff like that, or decimal places. Um, I would recommend when you look at these to take the rate that's in the table, and I would put the larger rate up on top. And that will just give you a little bit more whole numbers versus decimals. If you like decimals, you could leave them and do it either way, but it doesn't really matter. So for me, I see number 2 here has the higher rate. So I'm going to put that on top. So up on top is going to go everything from experiment number 2 from the table. So my rate is 4.8 times 10 to the minus 3, I think. Yeah, and meters per second. That's going to equal my K, which is my rate constant, which at this point I really don't know what it is. I do know the concentration of my F2 in that experiment is 0.1, and that is to the X. And I do know my concentration for the other one there is 0.04 to the Y. So basically everything I put in there all came from experiment number 2. I'm now going to do the exact same thing for experiment number 1 and put all those guys on the bottom. So coming through and putting experiment number 1's information there on the bottom gets me 1.2 times 10 to the minus 3 K, 0.1 molar for my F2, and 0.01 molar for my ClO2. Any questions on that? Now, again, you don't necessarily have to do it with the larger number up on top, but it does just kind of give you a little bit more whole numbers and decimals, but it will work if you kind of flip it around and put the first guy up on top and the second guy on the bottom. Now we got some math to solve for, so let us solve for this math here. When I divide these two, I believe I get a 4, so that's not too bad. Yeah. And at this point, I do not know the value of the rate constant up on top or on the bottom, but because it is a rate constant, should that number be a same number or different? Same as a constant. So although I don't know what it is, I do know they are going to cancel each other out. Since this is the exact same reaction we're doing, I don't know what this order is at this point, but it will be the same order on top and bottom. So this will essentially cancel out. And now that leaves me on the back end here dividing that, and that will give me 4 to the Y in this case. Now I could solve for Y. You could probably just see Y is equal to 1 in this case. Yeah. By the way, if you didn't have pretty numbers like that, you could take the natural log of both sides. And when you do that, the Y comes down and then divide it. And that's so in case you can run across a time where it's not nice, pretty numbers like that, and it's not super close to maybe round, you could natural log both sides and divide it is how you could solve for that if you needed to. Any questions on that? Yeah. So when you want to choose the experiments based on the concentrations where one stays the same and one varies. Once you've decided I'm going to go with like experiment 1 and 2, I personally would choose to put whichever experiment 1 or 2 has the larger rate up on top. And that's what's going to get you basically whole numbers. Because everything up here on top is all from experiment 2, and everything on the bottom is all from experiment 1. So really the decision is just to give yourself kind of more whole numbers, you probably want to put the one that has the larger rate up on top and with all the information that goes with it up on top and the smaller rate on the bottom. It doesn't really matter. You could do it the other way. You'll just get more of a decimal number rather than a whole number. So for a lot of people, working with just like a whole number is a little bit easier, but it will come out the same. But that's how I would choose to do it. Yeah. Other questions? Other questions? All right, so now that I do this, we now know that the order for Y, which is basically ClO2, is first order. Now what I'm going to do is I'm going to go back to my table, and I'm going to go back to my table, and now because in the first situation here, I kept the F2 constant, I'm now going to go back to my table and find 2 entries where the other reactant stays constant, the ClO2 now we want to keep constant. And if you look at the table, you could achieve that with experiment 1 and experiment 3 in this case will keep the other reactant constant and vary the F2 in this case. So the next one I'm going to look at is experiments 1 and 3. Again, that's going to keep this guy now constant and vary the other one. And we're going to kind of do the same deal. I'm going to look at experiment 1 and 3 and be honest with you, just choose whichever one maybe has the larger rate. So just looking at that, it looks like experiment 3 here has the larger rate. So for me, just to get kind of whole numbers, I'm going to put everything for experiment 3 up on top. Everybody's information for experiment 1 is going to go on the bottom. So if we do that here, we're going to get 2.4 times 10 to the minus 3 equals K. And again, all this is going to be experiment 3's information, 0.2 to the X, 0.01 to the Y. Now on the bottom, we're going to put all of experiment 1's information from the table, 1.2 times 10 to the minus 3, K, 0.1 to the X, 0.01 here to the Y. And now we're going to do our math again here. So we will divide this, and that's going to give us a 2. And again, you just get nice kind of whole numbers here to work with. Once again, still don't know what K is, but it should be a rate constant, so it should again cancel out. We actually already solved for Y. We know that those numbers on top and bottom are going to be the same, so they're going to cancel out. So at this point, we will end up with 2 to the X. And once again, here you could probably visualize here, X is going to equal 1. So for this reaction, the order for F2 is first order. The order for ClO2 is also first order. That, by figuring out those orders, will allow us to write the actual rate law, which is the rate is equal to K, F2 to the first order, and ClO2 also to the first order. The overall order in this case for this reaction would be what? Yeah, 1 plus 1, which is both orders added together, will get us an overall second order reaction at this point. First off, any questions up to there? At this point, once you figured out the orders, you can now actually figure out what is the value of the rate constant because that's the only thing you don't have. So at this point, what I could do is I could actually figure out what is the actual value of the rate constant. Now, where am I going to get all that information from? I'm going to get that information from the table here. You have the choice of choosing any entry in the table you like. You use experiment 1 information to do that, experiment 2, experiment 3. Because it is a rate constant, it should come out to be the same number. The only thing you can't do is mix and match. So whichever one you choose, you got to kind of use all that information. So for me, I'm just going to use experiments 1 information here. And I'm just going to put that now into my rate law where I'm going to solve for K. So K would equal the rate divided by the concentration of F2 and ClO2. And that is obviously rearranging this equation and dividing everybody to the other side, basically, the top equation there. Now, like I said, you could literally choose any entry in the table. So I'm going to go number 1 here, which means my rate is 1.2 times 10 to the minus 3 molar seconds divided by my concentration of 0.1 molar and my other concentration of 0.01 molar. At this point, we will now end up with 1.2 to the minus 3 divided by 0.1 divided by 0.01. Going to give us a 1.2 as our rate constant for this reaction. When we look at units, this is what's happening. The molarity up on top and one of the molarities on the bottom are going to cancel out. And you will be left with 1 over molar seconds, which are the units. Could also be written m to the minus 1, s to the minus 1 if you like as well. You could write it like that, the units. By the way, as you will quickly learn, those units that you see there are very much the units you find for the rate constant for a second order reaction. I won't give the hint away, but there's how many letters in that? 2. And it's a second order reaction. Maybe that's how that works. I don't know. But it kind of comes out that way. So those units are basically what we find for a second order reaction. And it's really important, obviously, to have the units and to know the units for K. As we will talk about in some later parts of this chapter, there will be problems where they will really tell you the order of the reaction, but they will give you the rate constant, and they expect you to know just based on the units of the rate constant what order of the reaction, and that will affect perhaps what formulas you might use later on in this chapter. Any questions on how to calculate that? All right. So as we just saw there, rate laws are determined experimentally, and the reaction are the rate laws always in terms of the reactants. Really no products are involved. And once again, a reminder, we do not use the coefficient as the orders. They do have to be found sort of experimentally through that table. As you can see here, the coefficient there is 2 for ClO2, but the order was only first order in this case. All right, so the rate equation for this reaction is the rate is equal to KNO times O3. If the rate is 6.6 times 10 to the minus 5 molar seconds, when the concentration is 1 times 10 to the minus 6 molar, and for O3, 3 times 10 to the minus 6. Okay, so let's take a look at it. So here they gave us the rate law. The rate is equal to K NO and O3. Again, when we do not see anything written there, that is first order there for our NO, and it's also first order for our O3. Again, nothing written means 1. Overall order here would be much like the last one there. It would be a second order reaction. So in this case, they actually gave us the numbers. So we just got to plug and chug in here. We're going to solve for K. Going to rate is equal to the concentration of NO and O3. Obviously, taking these guys and dividing it to the other side. Putting in our numbers, we got 6.60 times 10 to the minus 5 molar seconds divided by our 1 times 10 to the minus 6 and our 3 times 10 to the minus 6. Clearly, you want to make sure you are definitely using your exponent button when punching these in. 6.6 to the minus 5 divided by 1 to the minus 6 divided by 3 to the minus 6. Going to get us a 2.20 times 10 to the 7 in this case. And once again, the units here, molarity up on top, will cancel one of the molarities on the bottom. And that's going to give us, I'll just go underneath it, 1 over molar seconds. Once again, we see again the similar units that we saw in the previous one. That was also second order as well. Any questions on that one there? Okay, so why don't you try one here? Let's calculate the orders. What is the rate law? And what is the value of K? So based on the information in the table, We basically want to figure out the rate law, the orders, and the value of K. So take a few moments there, see what you come up with. Okay, let's take a look, see how you're doing. So we'll start with just kind of generically here, our rate law. So rate's equal to K times our first reactant there, S2 OA2 minus to the X and I minus to the Y. So once again here, we have three entries. By the way, you could have tables that have five, six, a ton of entries. But it still works the same way. You just want to choose two where we're going to keep one constant concentration and vary the other. And if you do have a table that has multiple entries, you may have multiple options as to which experiments to choose. They all should really give you the same answer as long as you kind of take that approach. So just looking at this, I can see one and two will keep this concentration the same and vary the other. So I'm going to start with that one. So we'll take a look at experiments one and two in this case. And once again, I'm going to take the approach of putting the one with the higher rate up on top, again, just to give me more whole numbers and decimals. So I'm going to put everything for experiment one here up on top. So 2.2 times 10 to the minus 4 equals K, 0.08 to the X, 0.034 to the Y. I'm now going to put everything for experiment two on the bottom, 1.1 times 10 to the minus 4, K, 0.08 to the X and 0.017 there to the Y. All right, so doing a little math here, that's going to be a 2. Once again, our rate constants will cancel. We don't know what X is at this point, but we do know it's the same, so it will cancel. And I believe that's a 2 on the back end there, so that's going to be 2 to the Y, and Y is equal to 1 in this particular case. Again, you get some pretty numbers here, but they're not always all nice, pretty whole numbers. Sometimes you may have some decimals and stuff like that that you might end up with. Now that we did that, we're going to go back to our table and isolate the other reactant. So we're going to keep the I minus now constant and vary the other. So we could do that with experiments 2 and 3. So we take experiment 2 and 3. Once again, looking at it, to me, experiment 3 has a larger rate, so I'm going to put that up on top. 4.4 times 10 to the minus 4 equals K, 0.16 to the X, 0.017 to the Y. Now everything for experiment 2 on the bottom, 1.1 times 10 to the minus 4, K, 0.08 to the X, 0.017 there to the Y. Doing our division there, that's going to give us a 4. They will cancel. They will again, over here will cancel. But here we will end up with, we got there 2, I believe, 2 to the X. At this point, we could solve for X, and you probably, again, can figure it out, but it does look like it should be, in this case, X is going to equal 2. Any questions on that so far? Now that we have both orders, we can write the completed rate law here. The rate would equal K times the concentration of S2O82 minus to the squared and our I minus here. That means in this particular case, the overall order for this reaction is, yep, third order. 2 plus 1 gives us third order reaction. And as I mentioned before, you kind of have to get the orders first. Now that you have the orders, you can then go back to the table now and actually solve for the value of K. So if we go back now here and solve for our rate constant, K will equal the rate divided by the concentration of S2O82 minus, you do have to square it, divided by I minus in this case. Yeah. I believe X was 2, if I didn't screw that up, hopefully. So the for me, the S208 was the first one that came out. Other questions? Again, in this case, you could choose any entry you want, and it should come out the same. So, I'll just choose the first one again, but you can technically do any of them up there. So 2.2 times 10 to the minus 4 molar seconds. divided by our 0.08 molar. We are going to square it. We're going to divide it by 0.3. Oops, lost a zero there. 0.034 molar. And we're not going to do anything to that guy. And that's going to get us here 2.2 to the minus 4 divided by 0.08 squared divided by 0.034. It's going to give us a 1.01. In terms of our units, a molarity up on top will cancel one of the molarities on the bottom. Will still leave you a molar squared second situation. Dare I say that's 2 M's and an S, that's 3 for third order. That's not too bad there. Any questions on that there? Yeah. It should. Let's say we'll do it just to make sure, but ideally it should. If I didn't screw with the numbers too badly. Let's go with number 3 here and we'll put it in there. So we take 4.4 times 10 to the minus 4 molar seconds divided by 0.16. That's the one we're going to square, right? And 0.017 molar here will be our K in this case. Let's see. Should, ideally. You get 1.01, yeah. Yep. Also, a reminder, if you are dividing stuff on the bottom, you may want to divide by the first number, hit equals, divide by the second number, and hit equals, rather than try to put it all in at once. Yeah. Other questions? Yeah, so absolutely, you could choose any entry in the table. They ideally all should give you the same K value. Yeah. Try another one here. Same deal. Let's do some rate law here. Some orders, some overall order, and the value of K. Yeah. Okay, let's take a look, see how you're doing. So in this one, we got a few more entries or a couple of extra entry in here. Again, works the same way. We're going to be looking for our orders first, as that will then allow us to get to our rate constant value. So I'm going to call it X and Y. Once again, just looking at this table, I can see obviously 2 and 3 here is going to keep my first one constant, going to vary my other. Not by much, but that is slightly larger, not very big. So I'm going to go with experiments 2 and 3 here to start with. I'm going to go with experiment 3 up on top. That's a 0.0083 equals K. And we got a 0.2 to the X and a 0.2 to the Y here. Going to put experiment 2 on the bottom there, 0.0082 K. Again, 0. We got there 2 and 0.1 there. All right, so at this point, if you do a little dividing, it is essentially 1. But again, as I mentioned before, since this is experimental type information, you may not get a nice perfect number. So here we didn't get a nice little perfect 1 perfectly here. And, you know, if you want to go with 1, you could round at this point, or you could leave it and we could decide what we want to do later. K, again, going to be the same on top and bottom. We don't know what X is at this point, but it will be the same on top and bottom. And obviously here we will end up with a 2 to the Y. At this point, like I said, if you wanted to, you could round out to 1, which would tell you that Y would be equal to, in this case, 0, right? So something to 0 order. Or if you're not sure, you could take the natural log of it and the natural log on the other side, and then divide that to the other side. Those will cancel. You basically take the natural log, that 1.01 number, divided by the natural log of 2. Yeah, if I could find 2 on my calculator, there it is. And that's essentially going to give you a Y that's equal to 0.0174, which is basically 0 as well. So again, it's fairly close to zero, you can round in this particular case. So if it is really close to kind of a whole number, you can round. Or if you did sort of the natural log, you probably would want to maybe round to the nearest whole number on it, which in this case would be zero in this case. Yeah. Any questions first off on that there? All right. So now that I got that one, we can go back to the table. And really on this second time around, we have like three different options you could choose. You could choose 1 and 2 would do it for you. You could choose 1 and 4. You could also choose 2 and 4, right? So again, it doesn't really matter which one you choose. They all should sort of give you the same answer. So for me, I'm just gonna go with 1 and 2 up here up front. And again, if you chose 1 and 4 or 2 and 4, you should hopefully end up with the same answer at the end. So looking at experiments here for me, 1 and 2, I'm going to go with 2 up on top as it's the larger value there, 0.0082 equals K 0.2 to the X, 0.1 to the Y. I'm going to put everything for 1 on the bottom, 0.0021 K 0.1 to the X and 0.1 to the Y. Once again, dividing here, not perfect, nice whole numbers. Get something like a 3.90476. Again, these guys are going to cancel. In the middle here will give you 2 to the X, and these guys at the end will completely cancel. So once again here, you can natural log both sides. Take the natural log of the number there equals the natural log of 2, bringing that X to the bottom, and then divide, obviously, back over that to the other side. So if you take the natural log of that big number there, 3.90476, you get like 1.36 divided by the natural log of 2. And that's going to get you an X value about 1.97, which once again is fairly close to a 2 in this particular case. Any questions on that? So again, like I said, they may not always be perfect numbers because technically they are based on experiments. And as you know from doing experiments, not always perfect, right? Numbers that you get as a result of that. So here our rate law would be something like the rate is equal to K and X was that. So NO2 squared. Now it's up to you. You can put the CO in here. If you choose to do so, you do need to write the 0 up on top. Because if I write the CO without the 0 on top, that implies it is what order? First order, yeah. So if you want to include a 0 order reactant in your rate law, you do have to put the 0 on top to indicate that it's not first order. Or it is fine as well. You could leave off it completely and just go with, the first guy there without the second one as well. So that's your other option. All right, so now that we have that, we're going to go in and solve for K. I'll go over here in this corner. K is going to equal the rate divided by my NO2 squared. Once again, we could go with any of the entries in the table to put in there. So I'm going to go with number 1, which will give me 0.0021 molar seconds divided by 0.1 molar squared. And that's going to get me there 0.0021 divided by 0.1 squared. Going to get me a perhaps 0.21. Unit-wise, a molarity on top and one of them on the bottom is going to cancel, leaving you 1 over molar seconds. Again, the typical units we see for like second order reaction, which is what this would be, right? This overall order of this reaction, 2 plus 0 is a second order reaction. And again, we see again our kind of typical second order units for the rate constant. 2 letters. Yeah. Any questions on that there? So again, if you don't have pretty numbers, but it's a very close number to a whole number, it's good. You're okay to round in most cases to that whole number. All right, one last one here to finish. Okay, let's take a look and see. So again, we'll start out here with our orders to try to figure out, and then work from there to get everything else. And a little generic rate law here. All right. So again, going to our table, looking to keep something constant. I can see 3 and 4 looks pretty constant there. So we can go with experiments 3 and 4 here. Once again, going to take kind of the larger rate there up on top. And that means I can put everything for experiment 4 up there. That's 21.6, by the way, times 10 to the minus 7, as that might be important since it's mentioned there in the table. If you miss that, you'll be okay for most of it, but probably not at the end. K is going to be times our concentration of 0.2 to the X and 0.0404 to the Y. We're going to do number 3 up there on top, also 10.8 times 10 to the minus 7. K 0.2 to the X and 0.0202 to the Y. Any questions on that one there? All right, so we do a little division there. It's going to get us a 2. This again is going to cancel. Not sure what X is, but will be the same on top and bottom. So they will cancel as well. And that's going to give us a 2 to the Y. So our Y here is going to equal 1 in this particular case. Now that we did that, we're going to roll into keeping the other one constant. And it looks like in this case, it's going to be 1 and 2 is going to do that there, those two. So we'll go experiments 1 and 2 in this case. And looking at it, it will be experiment 2 that's going to go up on top to kind of give me, again, a little bit more whole numbers. I'm not going to forget the times 10 to the minus 7 part. K are 0.06 to the X, 0.2 to the Y. Putting on there then everything for experiment 1, 10.8 times 10 to the minus 7. K 0.02 and 0.2. Doing our division here, we're going to get 32.3, 10.8. That's going to give us approximately 2.99 and some change. I'm going to call that a 3 at this point since it's pretty close to 3. Coming to the other side, we're going to cancel. And this is going to cancel. That's going to give us a 3 to the X. So it does look like X is going to be 1 in this case. So it is going to be first order for both reactants. So our completed rate law will look something like this. The rate is equal to K NH4 plus and NO2 minus. That will give us a overall reaction of order of 1 plus 1 should be second order. And at this point, once we have calculated our orders, we can calculate our rate constant. We're going to get that by rearranging. So our rate here divided by our NH4 plus and our NO2 minus. Now, if you sort of miss this thing here, this is where you're going to be in trouble because your number is going to be off here. The orders would have worked out fine because you missed on top and bottom, so that canceled each other out anyways. But here you do need that, so we'll go with number 1 there, 10.8 times 10 to the minus 7 molar seconds divided by 0.02 molar and 0.2 molar as well. Popping that in there using our exponent button here. Put it in correctly would probably be good as well, I imagine. Let's try that again there. Okay, looks like we're going to end up with 2.7 times 10 to the minus 4 unit-wise molarity on top and 1 on the bottom cancel, 1 over molar seconds. Again, you could also write that M1 to the minus M to the minus 1, S to the minus 1. And that would be it there. Question on that there. So Obviously, to calculate the orders, this is very common. What you will typically be given is, again, these sort of tables and the information in these tables that you kind of have to work in. Those are kind of the three common things you need to find: the orders, the overall order, the value of the rate constant. Any questions on how to do that there? All right. Well, seems like a good stopping place, I think, for now. So we will lay it up there for